What was the universe like immediately after the Big Bang? Most people imagine the Big Bang as a gigantic explosion that gave birth to the universe. But what if I told you that this idea is wrong? It wasn't an explosion in space. It was the very creation of space and time. In a fraction of a second, everything we know began expanding from an unimaginably hot and dense point. But what was that initial moment like? What really happened in the universe's first seconds? If we go back to the beginning of everything, we reach an unknown territory where the laws of physics no longer make sense. Gravity and quantum mechanics clash, and space-time behaves unpredictably. For decades, scientists have been trying to unravel this enigma, reconstructing the universe's first moments using the most advanced telescopes and particle accelerators. Yet, many questions remain unanswered. Did time have a beginning? Or was there something before? Did matter emerge from nothing? And how did a microscopic point become the vast universe we see today? To understand all of this, we need to dive into the deepest mysteries of science. And the answers may be even more surprising than you imagine. Have you heard about the Mars Climate Orbiter failure? In 1999, NASA lost a $300 million spacecraft due to a ridiculous mistake. One team used the metric system, while another used the imperial system. The result? The Mars Climate Orbiter entered Mars' atmosphere at the wrong altitude and was completely destroyed. A simple miscalculation, but with massive consequences. This failure proved that even the brightest minds in science can make fundamental mistakes without proper standardization. Ignoring small details leads to big problems. Whether in an interplanetary mission or in studying the Big Bang, the expansion of the universe, and distant galaxies, precision is everything, and this applies to life as well. Want to learn something new, like astronomy? Without a structured method, you'll get lost in endless information. Science doesn't work on improvisation, and anyone who seeks to understand the universe needs a well-defined path. Speaking of precision, Max Planck took this idea to another level by defining the universal constants that sustain all modern physics. Now, let's explain a little about Planck's universal constants. Imagine measuring the smallest possible unit of time, or the shortest length that can exist. It sounds like science fiction, but Max Planck did exactly that. In the early 20th century, he realized that some fundamental quantities of the universe could be expressed in terms of natural constants, such as the speed of light and the gravitational constant. Thus, Planck units were born, including Planck time and Planck length, the smallest possible values in physics. Planck time is so short it defies comprehension, 10 superscript 3 seconds. For comparison, a blink of an eyelash trillions upon trillions upon trillions of Planck times. In this infinitesimal interval, the laws of classical physics completely break down. Planck length, about 1.6 times 10 superscript 3 meters, is so tiny that even atoms seem gigantic in comparison. These incredibly small scales lead us to question the very nature of reality. Is space-time truly continuous? Or does it break down into something granular at these dimensions? It's like trying to see individual pixels on an ultra-high-resolution screen. The problem? We don't yet have the technology to investigate this extreme realm. The universe at the Planck scale remains an immense mystery. But one thing is certain. These discoveries were essential in understanding the first moments of the Big Bang. And if we want to reconstruct the beginning of everything, we need to look back and understand how the universe expanded from a single point. The universe, as we know it today, didn't always exist this way. It all started about 13.8 billion years ago, when a singularity, an unimaginably dense and hot point, burst, giving birth to space, time, and everything that exists. This epic event became known as the Big Bang, and from that moment on, the universe has never stopped growing. But don't be fooled into thinking this expansion is like an ordinary explosion. Matter wasn't just thrown outward into empty space. The very fabric of space itself started stretching, carrying everything with it. To visualize this, imagine a balloon inflating. The dots on its surface move apart, not because they are moving themselves, but because the surface is expanding. Now, replace the surface with space-time, and you have an idea of how the universe is expanding. The most fascinating part? This expansion is accelerating. Instead of slowing down over time, as one might expect, the universe seems to be pushed apart by a mysterious force. Dark energy. Scientists are still trying to understand this invisible force that counteracts gravity and drives galaxies farther apart at an increasing rate. Reconstructing the Big Bang's first moments is like solving a cosmic puzzle, and each new discovery brings us closer to the answer. But to understand the first seconds of the universe, we need to go even further, into an era where the laws of physics simply no longer work. The Planck Era, the universe's first moment. If we try to rewind time back to the very first instant of the Big Bang, we reach a point where everything gets weird. This moment is known as the Planck Era, a time when the laws of physics, as we know them, simply stop working. Planck time, 10^3 seconds after the universe began, marks a mysterious boundary where space, time, and energy blend in a way that science has yet to fully explain. Think of it as the Wild West of physics, where no rules apply. Fundamental forces had not yet separated, and space-time itself was a chaotic foam filled with unpredictable quantum fluctuations. If we had a microscope powerful enough to observe this fraction of a second, we would see something completely different from anything we know. The challenge of studying this era comes from the fact that Einstein's relativity and quantum mechanics are best tools for understanding the universe. Conflict at this extreme level. While relativity describes the universe on a large scale and quantum mechanics rules the microscopic world, neither can fully explain what happens during the Planck Era. To solve this enigma, we need something bigger, a theory that unites both, a quantum theory of gravity. But to get there, we must revisit the great minds of physics who shaped our understanding of space and time. And what about Newton's gravitation and Einstein's relativity? For centuries, Isaac Newton was the ultimate authority on gravity. His law of universal gravitation explained why apples fall and why planets orbit the sun. Simple, elegant, and incredibly useful. But there was a problem. Newton never explained how gravity actually worked. He could describe what was happening, but had no idea about the mechanics behind it. It wasn't until Albert Einstein came along that the pieces started to fit together. In 1915, he revolutionized physics with his general theory of relativity, showing that gravity wasn't a force in the traditional sense. It was the curvature of space-time. Imagine a trampoline. If you place a heavy ball in the center, it bends the surface, and smaller objects around it naturally follow that curve. In the universe, planets do the same around stars, and galaxies arrange themselves according to this invisible logic. Einstein didn't just improve our understanding of gravity. He completely changed how we see time itself. In his view, space and time are part of the same flexible structure, capable of stretching, contracting, and even slowing down near massive objects. This is why astronauts traveling at speeds close to the speed of light age more slowly than those who remain on Earth. This shift in perspective helps solve many cosmic mysteries, but not all of them. If relativity explains gravity at large scales, it completely falls apart when applied to singularities, such as black holes and the Big Bang itself. Something is still missing, and this is where one of modern science's greatest challenges begins. But the real challenge is singularities. Einstein gave us the best explanation of gravity we've ever had, but his theory has a serious flaw. It collapses in the face of singularities. And what are singularities? They are regions of the universe where the equations of physics break down completely. Black holes are a classic example. Places where density becomes infinite and space-time bends in extreme ways. But the greatest singularity of all? The Big Bang itself. This means that at the universe's origin, our current laws of physics simply don't work. It's like trying to divide a number by zero. It just doesn't make sense. Relativity helps us understand the cosmos on a grand scale, while quantum mechanics explains the microscopic world. But when we try to apply both to a singularity, nothing adds up. Gravity should behave like any other fundamental force, but we still don't know how to combine it with the quantum world. Without this unification, we remain in the dark about what truly happened in the universe's first moments. We know there was an expansion, but what existed before the Big Bang? Did space and time emerge from nothing? Current physics doesn't give us answers, only more questions. The key to solving this dilemma may lie in a fascinating and often misunderstood field: quantum mechanics. In the subatomic world, the rules are completely different. Particles can exist in two places at once, pass through invisible barriers, and defy traditional logic. And maybe it is precisely at this level that we will find clues about the birth of the universe. Did you hear about quantum mechanics and the subatomic universe? In the everyday world, things follow predictable rules. But in the quantum world, everything seems like a cosmic prank. Subatomic particles don't behave like tiny marbles. They act more like bizarre entities that can exist in two places at once, pass through solid barriers, and even influence each other without direct contact. This hidden reality governs the universe at its smallest scales. Take Heisenberg's uncertainty principle, for example. It tells us that we cannot simultaneously measure both the exact position and velocity of a particle. The more precisely we determine one, the more uncertain the other becomes. This means that, at the quantum level, nature itself imposes a fundamental limit on our ability to predict the future with absolute certainty. Another bizarre phenomenon is quantum entanglement. Two particles can become so deeply connected that, no matter how far apart they are, a change in one instantly affects the other. Einstein called this spooky action at a distance because it seemed to violate the very concept of space-time. Yet, modern experiments have confirmed that this effect is real, something that could be crucial for developing the quantum computers of the future. But the biggest question remains: how do we combine these strange quantum laws with gravity, which governs the universe on a massive scale? That's the next great mystery to solve. And the search for an answer leads us to one of physics' most ambitious goals: a quantum theory of gravity. The search for quantum gravity. Newtonian gravity worked well for predicting planetary motion, and Einstein's relativity explained the curvature of space-time. But when we try to combine gravity with the quantum world, everything falls apart. Quantum mechanics treats fundamental forces as interactions mediated by particles. But to this day, no one has found a gravity particle. Without this unification, we are still in the dark about what truly happens at the universe's most extreme scales. Two major theories attempt to solve this dilemma. The first is string theory, which proposes that all particles are actually tiny vibrating strings existing in multiple dimensions. Depending on their vibrations, these strings take on different identities, like electrons, photons, or possibly gravitons, the hypothetical particle of gravity. The problem? There is still no experimental evidence to confirm this idea. The second is loop quantum gravity, which suggests that space-time is not continuous, but instead made of discrete units, like pixels on a screen. If correct, this would mean that the very fabric of the universe is quantized. However, once again, there is no concrete proof for this hypothesis. The search for a quantum theory of gravity isn't just a theoretical exercise. Solving this mystery could help us understand black holes, predict the ultimate fate of the universe, and even reconstruct the first moments of the Big Bang. But testing these ideas requires technology far beyond what we have today. Even the most powerful particle accelerators on Earth are still nowhere near reaching these energy levels. Large Hadron Collider and quantum gravity limits. If we want to understand the universe at its smallest scales, we need powerful tools. And none are bigger than the Large Hadron Collider LHC, the world's largest particle accelerator. Located on the border of Switzerland and France, this massive underground ring smashes particles together at nearly the speed of light, allowing scientists to recreate conditions similar to those of the early universe. It was at the LHC that we discovered the Higgs boson, the famous God particle, which is crucial for explaining why other particles have mass. But despite its achievements, the LHC is still far from reaching the energy needed to probe the mysteries of quantum gravity. To investigate phenomena at the Planck scale, we would need a particle collider millions of times more powerful. In other words, we'd need a collider the size of an entire galaxy. Even with this limitation, the LHC provides valuable clues. Some experiments suggest that extra dimensions beyond the three spatial ones we know might exist. If confirmed, these dimensions could explain why gravity is so weak compared to other fundamental forces. The problem? So far, no concrete evidence of these dimensions has been found. So, if even the world's largest particle accelerator can't take us down to the Planck scale, how can we explore this unknown territory? One possibility comes from a theory proposed by John Wheeler. What if space-time itself is a chaotic, ever-changing structure when observed up close? This idea leads us to the concept of quantum foam, a possible fingerprint of the universe's first instant. The quantum foam and the universe's first moments. If we zoom into the smallest possible scale, space-time itself becomes unstable and chaotic. John Wheeler proposed that at these microscopic dimensions, the universe behaves like a bubbling foam, quantum foam. At this level, the classical laws of physics cease to exist and space-time fluctuates unpredictably. This means that, contrary to what we might think, empty space is never truly empty. Tiny virtual particles continuously pop in and out of existence, like fleeting bubbles in a quantum soup. Although imperceptible in our daily lives, this effect may have played a crucial role in the Big Bang's first moments, shaping the way the universe evolved from its initial state. But testing this idea is an enormous challenge. Quantum fluctuations in space-time occur at a scale far smaller than any experiment has ever been able to probe. Still, some theories suggest that this behavior might be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. If space-time truly behaves like quantum foam, it could explain why gravity still doesn't fit within the quantum model. But understanding this early phase of the universe requires something more. We need a theory that unites quantum mechanics and relativity. Without this fusion, many mysteries remain about what really happened in the first moments of the cosmos. Final mystery of the Planck Era. We have reached the limits of what science can currently explain. The Planck Era marks the closest moment to the Big Bang that we can reconstruct, but we still haven't been able to cross this barrier. Current physics simply cannot describe what happened at this earliest stage of the universe, a point where time, space, and energy were indistinguishable. The biggest challenge is uniting general relativity, which describes gravity at large scales, with quantum mechanics, which governs the subatomic world. Whenever we try to merge them, the equations break down, leading to absurd results, such as infinite values that make no physical sense. It's like trying to mix water and oil. No matter how much we stir, the two theories simply refuse to blend. Solving this mystery isn't just a theoretical endeavor. If we can understand the physics of the Planck Era, we may be able to answer some of the biggest questions in science. What existed before the Big Bang? Did time have a beginning, or is it infinite? Did the universe emerge from a singularity, or is it part of an eternal cycle of expansions and contractions? The answer hasn't arrived yet, but scientists continue to push forward. New experiments, such as increasingly powerful telescopes and more advanced particle colliders, may reveal crucial clues. After all, understanding the universe's origin is the first step in understanding its future, and perhaps even our own place within it. Now that you've explored the mystery surrounding the universe's first moments, take a step back and think. What else is hidden beyond what we've already discovered? If even science is still struggling to understand the cosmos' origins, how many more truths are waiting to be uncovered? The search for knowledge never ends, and each new answer only leads to even more fascinating questions. But now let me ask you this. Does the universe have a limit, or is it infinite? If space is constantly expanding, how far does it go? This question has puzzled scientists for centuries, and if you want to dive deeper into this enigma, watch our latest video. Is the universe infinite? There, we explore the most mind-blowing theories about the limits, or lack thereof, of the cosmos. And if you love this kind of content and want to keep exploring the universe's secrets, don't forget to subscribe to the channel and turn on notifications. That way, you won't miss any new videos and can continue this incredible journey into the unknown.